Yes, today I am going to discuss uh, um, a lecture. I'm going to give a lecture about steel production. And the topics I'm going to talk about today is the production of slag. As a metallurgical engineer, I am giving this lecture for those who are undergraduate, graduate students who wanted to advance their skills in metallurgy. So how is slags produced? Four things I am going to discuss about the making of slag, all smelting, ancient slag use, modern slag, modern slag use, and basic slag. Those are the four topics I'm going to discuss about today. So, what is a slag in the first place? Slag is a partially vitreous byproduct of the process of smelting ore. This ore is in a liquid form, and we get iron ore from Itape. So referencing to Nigerian situation, which separates the desired metal fraction from the unwanted fractions. Slag is usually a mixture of metal oxides and silicon dioxide. However, can contain slag can contain metal sulfides. That's metal sulfides, which is and a metal atoms in the element form. While slags are generally used to remove waste in metal smelting, they can also serve other purposes, such as assisting in the temperature control of the smelting and minimizing any reoxidation of the final liquid metal before the molten metal is removed from the furnace and used to make a solid metal. So that's the definition of slag. Now, ore smelting. In a nature, the ores of metals such as iron, copper, lead, nickel, and other metals are found in impure states, often oxidized and mixed with silicates. Other metals during smelting, when the ore is exposed to high temperature, these impurities are separated from the molten metal and can be removed. Slag is the collections of compounds that are removed in many smelting processes. Oxides are introduced to control the slag chemistry, assisting in the removal of the impurities and protecting the furnace refractory lining from excessive wear. In this case, the slag is termed synthetic. A good example is steel making slag, quicklime, and magnesite are introduced for a refractory protection, neutralizing the alumina and silica separated from the metal, and assist in the removal of sulfur and phosphorus from the steel. Ferrous and non-ferrous smelting process produce different slags. The smelting of copper and lead in iron ferrous smelting, for instance, is designed to remove the iron and silica that often occurs with those ores and separates them as iron silicate based slags. Slags from steel mills in ferrous smelting, on the other hand, is designed to minimize iron loss and so mainly contains oxides of calcium, silicon, and magnesium. In this case, an aluminium Any sandy component or quartz component of the original ore automatically carries through the smelting process as silicon dioxide. As the slag is channeled out of the furnace, water is poured over it. This rapid cooling, often from a temperature of about 2600 degree Fahrenheit, which is approximately about 1430 degrees centigrade, is the start of the granulating process. The water carries the slag in its slurry format to a large agitation tank, from where it is pumped along a piping system into a number of gravel-based filter beds. The filter beds then retain the slag granules while the water filters away and is returned to the system. When the filtering process is complete, the remaining slag granules, which now give the appearance of coarse beach sand, can be scooped out of the filter bed and transferred to the grinding facility, where they are ground into particles that are finer and Portland, like a Portland cement, or like any kind of cement factories where they produce cement. You know, cement are very fine granular, so that's how it will look like. So in the next phase, I'm going to address the ancient slag use. During the Bronze Age of the Mediterranean time, there were a vast number of differential metallurgical processes in use. A slag byproduct of such working was a colorful, glassy, vitreous materials found on the surface of slag from ancient copper foundries. It was primarily blue or green and was formerly chipped away and melted down to make a glassware, products and jewelry. They use it in those days to make jewelry. It was also ground into powder to add to glazes for use in ceramics. This is done in Egypt. That's an ancient slag. Historically, the resmelting of iron ore slag was common practice, as improved smelting techniques permitted greater iron yields, in some cases exceeding that which was originally achieved. During the early 20th century, iron ore slag was ground to powder and used to make agate glass, also known as slag glasses or glass. So those are the history, the ancient slag, the use of slag during our olden days time, or we call the ancient age. Let's look at the modern slag, modern use of slags today. In this case, ground granulated slag is often used in concrete in combination with a cement as part of blended cement. Ground granulated slag reacts with water to produce cementitious properties, become very symmetrical, very hardened. Concrete containing ground granulated slag develop a strength over a longer period, leading to reduced permeability and better durability. Since the unit volume of the cement is reduced, this concrete is less vulnerable to alkali silica and sulfate attack. This previously unwanted recycled product is used in the manufacture of high-performance concretes, especially those used in the constructions of bridges and coastal features, where it is low permeability and greater resistance to chlorides and sulfates can help to reduce corrosive and action and deteriorations of the structure. The slag can also be used to create fibers used as an insulation material named slag wool. Now, the next thing I'm going to talk about in this very particular lecture is the basic slag. What is basic slag? Basic slag is a byproduct of steel making using the basic versions of the Bessemer process. We use the Bessemer process in the basic slag, or the Linz-Donawitz process. It is largely limestone or dolomite, which has absorbed phosphate from the iron ore being smelted. Because of the slow release of phosphate content and because of its liming effect, its values as fertilizer in gardens and farms in steelmaking areas. According to the American Association of Plant Food Control officials, basic slags must contain at least 12% of total phosphoric acid or be labeled low phosphate. Now, let's look at the dross. We talk about let's look at the dross in this case. Yes, in talking about the dross of steel, what is dross? So we have to really analyze to know what dross means. In steel making, we have series of things that comes to light when we are making steel, which is very important. Those are dross, fly ash, and granulated blast furnace slag. And we also have what we call pozzolan and spoil heap tailings. In this case, in looking at all of this will help us in our steel making. In order for us to continue to work on the steel and to talk about how steels are being produced, so we need to be able to address all of those things, which is the dross. We will talk about the dross. We will talk about every other things regarding, what will the properties of steel making, of the slag. We'll talk about the property of slag. Then we will also discuss about every aspect of this steel production, which you are almost aware about. So the next one that I said I will address was the dross. What is dross? Dross is a mass of solid impurity floating on a molten metal or dispensed in metal, such as in wrought iron. It forms on the surface of a low melting point. Metals such as tin, lead, zinc, aluminum, or alloys by oxidation of the metals. With wrought iron, hammering and later rolling removes some dross. With the tin and lead, the dross can be removed by adding sodium hydroxide, which are called the pellets, which dissolve the oxides and from a slag. Dross can also be skimmed off. So dross as a solid is distinguished from slag, which is a liquid dross. which is a liquid. Dross product is not entirely waste material. Aluminum dross, for example, can be recycled and used in secondary steelmaking for a slag deoxidation. Now, under this, we will talk about the etymology and usage. The term dross derives from the Old English word dross, meaning the scum produced when smelting metals. By the 15th century, it had come to refer to rubbish in general. Dregs, the geological term, dross, are also thought to be etymologically related. Metallurgical dross is referenced as a metaphor for worthless material in the Bible and in other religious texts. So when you say dross, they look at it that, okay, this is a worthless material, basically. Now, let's look at, in this case, the aluminium. Let's look at the aluminium dross, in this case. Aluminium alloy inclusions. We will talk about the aluminium ion inclusion, and then you will see exactly what does that entails. So under aluminium ion inclusion, we will talk about inclusion type, we will talk about inclusion measurement, we will talk about inclusion removal. Now, problem related to inclusion. An ancient inclusion is a solid particle in liquid aluminum alloy. It is usually non-metallic and can be different nature depending on its source. Problems related to inclusion. So let's look at the inclusion types. We have oxide fumes, we have aluminum carbide, we have magnesium oxides, we have refractory materials, we have chlorides, we have fluoxine salt, we have internationally added inclusions, and we have less frequently found inclusions. So let's address this problem related to inclusion. Inclusion can create problems in the casting when they are large and too high concentration. Here are examples of problems related to inclusion. Pinholes in light gauge foil. Next, flange cracks in beverage containers. Breaking in wire drawing operation. Increased tool wear and tear. Increased porosity. Loss of pressure. Tightness of engine blocks. Machinability and cosmetic defects in apparent surface. These are the problems that is related to inclusions. Now, let's talk about the oxide fumes, these are the inclusion types. In contact with ambient air, which is air, liquid aluminum reacts with the oxygen and form oxide film. Oxide film layer. This oxide film layer is called gamma aluminum oxide. This layer becomes thicker with time. When aluminum is moved, this oxide film gets mixed inside the metal. So let's look at about the aluminum carbide. In primary aluminum production, aluminum carbide, which is aluminum carbide, originates from the reduction of alumina, where carbon anodes and cathodes are in contact with mix. Later in the process, any carbon stools in contact with the liquid aluminum can react and create carbides. Then we also have the we also now have what we call in aluminum oxide. In aluminum oxide, in aluminum alloys, which is the alloys now containing magnesium and magnesium oxide, cuboids and metallurgical spinel can form. They result from the reaction between magnesium and oxygen in the melt. More of them will form with time and temperature. Spinel can be highly detrimental because of its big size and high hardness. Refractory materials. Particles of refractory materials in contact with aluminum can detach and become inclusion. We can find graphite inclusion, alumina inclusion. After some time, graphite refractory in contact with aluminum will react to create aluminum carbide, which is harder and more detrimental inclusion. So here we're going to talk about another thing we're going to talk about is the aluminum alloy containing magnesium. The magnesium reacts with some refractories to create rather big and hard inclusions similar to spinels. Unreacted refractory particles coming from the degradation of refractory materials which comes in contact with melt. Let's look at chlorides in this case. Chloride inclusion, which is magnesium chloride, sodium chloride, carbon chloride, are special type of inclusions as they are liquid in liquid metal. When aluminum solidifies, they form spherical voids similar to hydrogen gas porosity. But the void contains a chloride crystal formed when aluminum became colorful or colder, when aluminum become colder. Fluoxine salt, which also part of the refractory materials. The fluoxine salts, like chlorides, are also liquid inclusion. They come from flux treatment added to the method of cleaning. Intentionally added inclusion. These are inclusions that are intentionally added. A titanium boride is intentionally added to the melt for grain refinement to improve mechanical properties of steel making. This phosphorus is also added to the melt, which is hyperelectric alloys from modifications of the silicon phase for better mechanical properties as well. This creates AIP inclusion. Boron treatment inclusion. From when boron is added, this method to increase conductivity by precipitating vanadium and titanium. Less frequently found inclusion. The following inclusion types can also be found in aluminum alloys, aluminum needles, the nitrides, the iron oxides, the magnesium oxides, the fluorides, the aluminum borides, and bone ash. Inclusion measurement. Under inclusion measurement, several methods exist to measure the inclusion content of the liquid aluminum. The most common methods are PODFA, Prefil, K-mode, and Limca. Measuring the inclusions of the great help to understand the impact of the furnace preparation and alloying practice, feedstock mix, and smelting time, and similar parameters on smelt cleanliness. The PODFA, which we call PODFA, The POTFA method provides information on the composition and concentration of the inclusions in the molten aluminum. POTFA is widely used for process characteristics and optimization, as well as product improvement. It allows us to quickly and accurately assess the effects of the various operating practices on metal cleanliness or identify filtration efficiency. The POTFA method was developed by Rio Tinto Alcan in the 70s. This metallographic analysis method has been optimized for over the years on a wide variety of alloys. The measurement principle in the following is the following. We have the predetermined quantity of liquid aluminum filtered under controlled conditions using a very fine porosity filter. Inclusion in this melt are concentrated at the filter surface by a factor of about 10,000. The filter along the residual metal is then cut, mounted, and polished before being analyzed under optical microscopic by trained POTFA metallographer. Prefill. The prefill method is similar to POTFA. In addition to the metallographic analysis, prefill provides also an immediate feedback on the metal cleanliness from the metal flow rate through the filter. Because everything about the filtration is well controlled, pressure, metal temperature, the only parameter affecting the filtration speed is the inclusion content, or can determine the cleanliness level of the filtration curve, weighing of metal filter as a function of time. Let's look at the K-mode. The K-mode is a fracture test method. Liquid metal is cast into a mold containing notches. Once solidified, the resulting bar is bent to expose the fracture surface. The visual observations of inclusions on the fracture is used to determine a K value of the melt and compared to a preset standard. This method is rather precise and therefore only suitable when metal contains large inclusions and inclusion clusters. Then I will address again what we call the linker. The linker method measures the total concentration and size distribution of present aluminum alloys. Its measuring principle is based on objective user. Independent method, the Limca CM system can characterize the cleanliness of a melt at time intervals in order of 1 minute. It can be therefore monitored in real time the evolutions of cleanliness along cast as a function of process parameters and smelting handling practice. So we talk about the heart of the Limca. For the heart of the Limca measuring system consists of a closed glass tube, electrically insulating material bearing a small orifice at its bottom. The tube is positioned in a liquid metal by creating a vacuum. Inside the tube, the metal with suspended inclusion to be detected is forced through the small orifice. 2 electrodes are necessary, one inside the tube and the one outside. Both electrodes are immersed in the liquid metal. a constant electrical current is applied between the electrodes. The current flows through the liquid metal by the small orifice in the tube. When the inclusion enters into orifice, it displaces its volume of conducting fluid, temporarily arising electrical resistance. The increase of a resistance generates a voltage pulse. The magnitude of the voltage pulse is a function of the volume of particles. The durations of the pulse is related to the transit time of the inclusion. The voltage pulse are amplified with their amplitude measured digitally. The size distribution, total concentrations are displayed in real time on a computer screen. So, inclusion removal. In dealing with the inclusion removal, in order to get a good quality product, removing the inclusion becomes necessary. Liquid metal filtration through a ceramic media is an efficient way to clean the metal. Different types of ceramic media are used in the line of foundries, such as ceramic foam, filter porous, tube filters, and bonded ceramic filters, and deep bed filters. On my next topic that I will address, which will be the part 2 of my lecture, will consist of non-metallic inclusions and the hydrogen gas porosity. So for today, I'm ending this lesson. For those of you who want to read metallurgy, if you listen to this lecture that I've just given, it will give you an insight of how steels are being made, right from the iron ore. You get the iron ore into producing the slags, and and all of other things that you need to know in steel production. So stay put and watch part 2 of steel making. Thank you. God bless.